So how many of you are below age 10? Oh, nice. Like kids are sacrificing their Sundays for science. That's really great. Below 15 age. Oh, wow.
And above 40? Nice.
Wow. We have all the age groups.
Good. Okay, Survi, stage is yours.
Yeah, thank you. Is there a
Yes, there is. There is. Upper ka pointer and then up and down. Don't
this
use
is
these
the
two.
pointer?
This
Don't
two.
not to use these two.
Not to use these two, only these two.
Okay, I'll figure. Okay. So hi, good afternoon, everyone. I'm Surbhi, and I work in low energy electron molecule collisions, and particularly I'll talk about the physics of collision. So before I start with my talk, let me give you a glimpse of the types of things. Okay, it doesn't work. Yeah. Yeah. So the kind of, let me give you a glimpse into the kind of things we might be able to answer, too ambitious, but maybe at the end of this talk. So do the laws of physics change at different scales? So when you go from, suppose, a very macroscopic system to a microscopic system, does the physics of how the systems behave change? Then we keep on hearing in news that there is some molecule like water or oxygen discovered in some planetary systems or some interstellar medium. So how do we actually know that they exist there without directly observing them? Is it possible to do that? Then another thing that we precisely in our lab try to understand is controlling chemical reactions. So chemical reactions is, as we would understand it, as making and breaking of bonds. So is there a way that we can control which bond to break in a molecule? And it will have huge applications in the industry, of course. So before I go to the molecular level, let me just talk about collisions. What are collisions? Collisions are basically two bodies coming towards each other with some velocity. And like for the case of a billiard ball, it'll just collide and go away from each other. And it can also be of the type of here, the bullet colliding with a hard wall, where it just shatters. So these are two, both of them are collisions, but they can be classified differently. So there is one elastic collision, which was the case of the billiard balls colliding, where you would have maybe if I don't know, maybe 9th standard students and above would remember seeing these kind of diagrams in their physics books, where you describe these processes in the terms of the momentum of the particles colliding, the masses of the two particles, and their velocities with which they're coming towards each other, and with what velocity do they separate out. And the interesting thing about elastic collision, the thing to remember, is that in elastic collisions, the kinetic energy of the system is conserved and the momentum of the total momentum of the system is conserved, where they're given by these expressions. Now, there is inelastic collision, for example, in the case of a car crash, where the two bodies come and then they just they disfigure like a car accident. Exactly. So this is, this comes in the case of inelastic collision. And for these collisions, only the conservation of momentum occurs and not the conservation of the total kinetic energy. However, the total energy is always conserved. It maybe just goes in this case into the disfigurement of the bodies. Now, if I more or less know these things, momentum and kinetic energy about these systems, then I would be able to predict what would happen in these collisions at all times. One very interesting case of elastic collision is the collision of ball against a wall. So have we ever thrown a ball against a wall? It bounces back. Exactly. So it always comes back to me with the same velocity that I sent it with. So the ball doesn't move at all. Right? So this is like how it looks. So the momentum mu1 is the initial and mu2 final, which are both just equal and opposite in direction. And the wall, which is here like capital M, the mass of the wall, it's much heavy and it doesn't move. So like, will it always happen? So yes, it will always happen. And we know this by doing some physics, and I'll just flash the equations, but I mean, these are very simple equations, but we don't need to go into the details of them. But there is momentum conservation, there is energy conservation, and now for this particular system, I know that the wall is stationary. So U2 is 0. So for such systems, the velocity of this small object comes out to be this, and the other object comes out to be this. And now, just the important part is that these velocities, V1 and V2, only depend upon the ratio of the two masses and not on the actual masses of the two colliding bodies. And that is why no matter what, no matter what is the size of the ball that you throw at the wall, it comes back to you with the same force. Okay. So the ratio of M by M is all that matters. So if I go to a smaller ball and a smaller ball, again, this thing would happen. So now, is this the fundamental thing? Like, is the ratio all that matters? Will this always happen? Is the kind of question that physicists ask. Like, if you keep on making this system smaller and smaller, if the ratio of masses don't change, then will it always happen? So by making it smaller, I mean, let's just go to the most fundamental particles, where which the most fundamental particles that compose the matter. So so suppose like electrons and atoms. So I'll come to that, but before that, there is a question. So of course, do we know that there are only 4 fundamental forces in the universe? Have we ever heard this before? No, but so so there are only 4 fundamental forces in the universe, and it is only one of these that is acting when any two bodies interact. So can someone tell me which are these 4 forces, if anyone knows? Gravitational force, of course. No, those are not the fundamental forces. Exactly, electrostatic force. That comes in electromagnetic force. Again, electromagnetic force. What? Did someone say strong force? Yeah. Okay, weak. Sorry. But also weak force. Okay. So, and like, you may not have questioned this ever before because it's not required. But when two bodies collide, it is the electromagnetic force which is working. Now, when you want to keep on going to the most fundamental sort of collisions, that is when you need to invoke this force to understand how those things work. So why I mentioned the ball and the wall problem is because this is very similar to the case of an electron colliding with a molecule. So in this case, it's just an oxygen molecule. So it's very similar. Why? Because some of us would know that electron is much lighter than a molecule, and therefore, so if the ratio of mass is all that matters, will the electron just bounce back? What do you think? Yeah, no. So the problem is more involved in this case. So before I go to that, for the people who may not be very familiar, I'll just talk about what is a molecule. So before talking about what is a molecule, I need to talk about what is an atom. So atom is, this is a textbook picture of an atom where there is a strong positive core composed of a small positive core. Yes, and the positive core is made up of protons and neutrons. And then there are very light electrons that form a cloud around this nucleus. And when these atoms come together, they can form very specific bonds and make up molecules. Common examples of the molecules that we know are water, ammonia, carbon dioxide, methane. We would have heard these names. And this is how their structures look like. Now, again, electron is 1800 times lighter than a proton. So it is much, much lighter than a molecule. So it is, so what happens in this kind of collision? So, we cannot understand these collisions very simply. We need to invoke the wave nature of the electron when we want to understand such fundamental interactions, where you can consider the wave electron to be a plane wave colliding with, suppose, two spheres here. So think of it as like water against two spherical balls, but of course much, much lighter. But the electron behaves as a particle when the wavelength of this of the electrons is about the size of the atom. So in these kind of processes, we need to consider the most fundamental force, which is the electromagnetic force. So we understand what happens based on what is the electron-electron repulsion, what is the electron and the nucleus attraction, and then invoking the principles of quantum mechanics. So to sum up, the usual laws of the macroscopic world do not hold in this regime, and quantum mechanics comes into the picture, and the electron may or may not bounce back, unlike the case of a ball against a wall. And the outcome is probabilistic. That what it means is that maybe there is there are n number of processes that can happen, and all of them will happen with some probability. There is no one particular outcome that will always come. And this is something I've just written down, but I won't be able to discuss. But there can be superposition of these outcomes happening all at the same time. Now, because I work in electron scattering, scattering is just a different name for collisions we give in this field. So there are, what are the types of electron scattering? So of course, like in the case of elastic scattering that we saw in our macroscopic regime, in which the electron just comes and doesn't interact much with the molecule, just deflects a little and doesn't exchange any energy with the molecule. There can be inelastic scattering, where the electron comes, dumps some energy into the molecule and passes by. Now, this molecule is now more energetic than it was before. And there is this special case called resonant scattering, which is not something that ever happens in the macroscopic world. So resonant scattering is only a quantum mechanics phenomena in which the electron can just bind with the molecule for some time and make a temporary negative ion. And and these temporary negative ions are what we study in our laboratories. So I've just listed out all the various things that can happen when electron molecules collision happens. There can be elastic, broadly there can be elastic scattering, inelastic scattering, and resonant scattering. And in the case of so these, basically, why are there so many processes that happen? Because now the electron, for the case of inelastic and resonant scattering, has given some extra energy to the molecule. Now this molecule with this extra energy is not necessarily stable. So it needs to give out that energy. It can do that in various ways. It can just emit out a photon, or the electron that is at, or it can break off with that extra energy. Just a bond in the molecule breaks off. So all of these processes happen, and I particularly study dissociative electron attachment, where the electron comes, binds with the molecule, and this molecule is now unstable. It is a negative ion which is unstable, and it dissociates into a neutral and a negative ion fragment, or maybe more fragments, like not just necessarily two if it is a bigger molecule, polyatomic atom. What? No, because now you need to talk about the electromagnetic force and the electron-electron repulsion and the electron and the nucleus attraction. These things you never worried about when you talked about ball against the wall. You just had simple kinetic energy conservation, momentum conservation, and you always knew what happens. In this case, it's way more involved. Now, as we talked, like electron comes, and this dissociative electron attachment happens for very low energy electrons, which is electron passes by the molecule, has enough time, spends enough time near the molecule and gets attached to the system. But the most important thing about why I mentioned resonance is because it only happens for certain specific energy of the electron. It doesn't happen for all the electrons. Electron with a very specific energy can come and bind with the molecule. And this molecule decays by a fragmentation. And if AB was the initial state of the molecule, the ground state as we call it, and AB minus is the state where it will come to after the electron attachment. So the energy required for this excitation to happen comes from this electron. So only if the energy of the electron matches the energy between these two states is when this process occurs. Okay, another thing is that, remember in the beginning of the talk, I talked about control. So an interesting thing comes out from here. If I can control the energy of the electron that is interacting with the molecule, I can dissociate a particular bond in the molecule. So a molecule can be, for example, like molecule water, which is a very simple case. But now think about a molecule like alcohol, okay, which has OH bonds and CH bonds and multiple of them. And now if I can control, if I find a way to just break the OH bond, the H coming from the bonded with the oxygen atom and not the CH bond, then it's a very useful thing to do. And this is the kind of control that we can get from here. And well, actually the process is more involved. I'll just put on a picture here that the energy levels are actually these potential energy surfaces. And yeah, the molecule evolves on this potential energy surface. I'll not go into the details of it, but just mentioning. So I want to understand this process of dissociative electron attachment. So what are the things that I need to know? If I want to understand this process, what do I want to know? What are the fragments that are formed, right? Identify the anion. So now I'll talk about how do I do that in my experiments. So we in our experiments use something called a time of flight mass spectrometer, where the negative ion that is formed in this dissociation. So how can I make this negative ion? So suppose the negative ions are formed in this region. I can push these negative ions outside of this region and take them to the detector and detect what these ions are, right? can someone suggest a way? How can I push an ion out from a particular reason? Like is there can you? Exactly, by applying electromagnetic fields. So if I have let's say a repulsive field that pushes this ion out, then I'll be able to take it to the detector. So this is what we do. Now, how do we know what ion came? What we look at the detector is the time that the ion took to come to the detector. Now, a heavier ion will come slowly to the detector and the lighter ion will come fast. And if I know the time taken by these ions to come, I in a way know the masses of these ions. And if I know the masses of these ions, I know what these ions are. So now we know what these ions are. The other things to describe the dynamics of this whole process are what are the energies involved in it. And I need to know the energetics, the ions, what energy did it come out? What direction did the anion come out of? So angular distributions. And as I mentioned before, these processes are probabilistic. So what is the probability that this will happen, that this particular bond will break? And which is called cross sections in our field. So this is how the schematic of how my experimental setup looks, where there is an electron gun, and this electron gun sends an electron of a specific energy, and it collides with molecules that are coming through the capillary, and this is single electron molecule collision. So the pressure in the chamber is so low that only one electron interacts with one molecule. And then there are these negative ions that are formed here, which I can project onto the detector in that via the technique that we looked at before. And this way I'll have so many interactions happening there, and I'll form an image like this on my detector where the ions hit. And this is an actual picture from one of the experiments of how the image of these ions hitting at the detector look like. From this image, I can find out what is the energy of the ion, and therefore the energetics of the whole process, and what is the angular distribution, which is important to understand these processes. So this is what we do in our experiments, basically. And this is just a setup from our laboratory. This is the collision chamber where all of this happens. And this is just this electron gun is what sits inside these chambers. And there are a lot more parts to it. But so these electron guns send you the monoenergetic electrons. And this is how it looks. And okay, in the beginning, I just talked about certain things. So I think few of the questions you get the answer to, like, do the laws of physics remain the same at different scales? Of course, the laws of physics do not change, but we need to invoke new principles when we go from one scale to another. Then, okay, and there is this thing that I mentioned about how do we find out that there are particular ions or molecules in a interstellar medium when we do not go and directly see it. So when we understand how these interactions happen at a single collision, single molecule electron level, then we can predict what will be the outcome of these interactions. And therefore, if I can detect some ions or some molecules, I can predict what else can I detect over there. So this is how those predictions are made. And of course, I mentioned about selectively breaking bonds. So I explained it that like you can choose the energy of the electron and break a particular bond. And this is something that is called functional group site selectivity in our field, which came from our lab. And then there is another reason why we study these things is because like radiation therapy is very common form of treatment for tumors and all these days. And these radiation is basically just a bunch of photons interacting with your tumors. And these high energy photons, they create a lot of electrons. And these low energy electrons that are created from that process can cause bond breaking in molecules, as we saw, and they can break the DNA strands, and therefore it is very important to understand how these low energy electrons interact with DNA or organic molecules in general. So these are the things that I wanted to talk about. If you have any questions, you can come at me.
Thank you, Survi. So yeah, the podium is open for questions.
Yeah.
Yes. Front.
Can we go back to the slide of decay by fragmentation?
This one?
Yeah. So what is the backward and forward angle there?
Okay. So backward and forward angle is that this fragmentation happens in a certain orientation with respect to the direction of the electron. So in my experiments, the direction of the electron beam is fixed. And so this is that. Yeah, good question. Yeah. How does an electron gun work? Yeah. Yeah. So that's. I guess I just showed us this. I could have shown a schematic, but yeah, how does an electron gun work? You create electrons. How do you create electrons? So just a tungsten wire, a thin tungsten wire, if you heat it a lot, it will emit a lot of electrons. That is called thermoemission. So it will emit a lot of electrons. And now you have all these electrons, but you want these electrons to be of a specific energy. So if you can accelerate these, if you can somehow provide them this energy, then you have the energy of, that energy electron. So what we do is we create these electrons using a tungsten filament, and then we accelerate these electrons and give them the respective energies. And that's how we get a monoenergetic electron beam.
Any more questions?
So Surbi, I have one question.
Yeah.
Can I kill someone with electron gun?
It only works in vacuum, so no.
Yes, we have.
Yeah.
another.
Electron accelerated in the electron gun and it emits electromagnetic radiation then? That's my question.
It doesn't emit electromagnetic radiation. It emits electrons. Electrons now.
So it amplifies the electrons, the energy of electrons.
No. So the energy of the electron you give in a different process. The emitting is one process. You heat up something and it just throws out electrons. Okay. And then once you have these electrons, you give them some energy. How do you give them this energy? Is by applying electromagnetic fields. Like,
So by
you give.
accelerating?
Yeah.
By accelerating?
By accelerating, I mean giving them accelerating. I mean, let's say I have an electron and I put a electrode behind it, just a plate behind it, and I make this plate negatively charged, which means this electron will now go away from it.
Yeah.
And by controlling this electric field, like the electrodes and what field I send to it, I can accelerate my electron by a certain fixed amount.
Okay, thank you.
Questions?
Surbi, I have one more question. So what are these weak and strong forces you were talking about? Is it like this is weak force and this is strong force?
So weak and strong force, I'm not an expert. These are the forces which you would generally not have to worry about unless you do very high energy physics, because these are the forces that that are between the nucleus. Okay, they bind the protons and neutrons, and then like these proton and neutrons have their own substructure,
Right.
and it is bounded by weak force and
I think
strong
quark
force.
and gluons are the interacting particles, and in the
Okay, so
case
it
it's
is
double boson.
within the
It
nucleus.
is within the nucleus that these forces occur. They have a very
We cannot like without it's having very high energy, we can't.
With
peek
very
into
high
it.
energy, we can probe these things, but we work with low energy electrons. So I'm
Exactly.
not an expert, but yeah.
Okay, so once again, let's thank Surbhi for this wonderful talk. Great.
Okay, thank you.
So, yeah, so we have